Hi.
Hi there. There it goes. Okay.
Afternoon, Professor.
Hey, how are you? How's the weather over there?
I'm sorry?
How's your weather?
Not great.
This is 8321, so it's open. All right, cool. All right, I'm actually posting just in case we lose connection because of the weather. I'm gonna post the copy of what I'm gonna go over today. I think I have it. If I don't, we're out of luck. I don't think I have it. I have everything else. 4, 3, 4, 2, 4, 4. I do have 4, 1. All right, let me copy these so we have them. Lovely. All right. Oh yes, so this weather is not very good. So we're in chapter 4. We have 4-1, 4-2, 4-3, 4-4, 4-5 to do. And then we'll have a quiz on that section. I saw most people did really, really well on the section that we just covered, so that's good. So I'm gonna go ahead and share my screen. And we're gonna start with 4-1. Now, if time permits, I don't know what your energy is like. I'd like to do 4-2 if possible. If you want to just do one at a time, that's fine too. I don't think we need to necessarily do both. All right. So we're going to start with 4-1, which is all about exponential functions. And it sets up our platform for discussion. Can everyone see the screen without issue? Or do you know?
No, you're not sharing something.
Okay. You should be able to see my screen now.
Yeah, we're good.
Basically a blank screen. All right, so exponential functions. You will need a calculator for parts of this lesson. The majority of it will not require a calculator, except for exactly the first question. That's what I wanted to do, but maybe 4-2 and 4-1 at the same time. So we're looking at section 4-1. It's all about exponential functions. And the first example they give us is merely a question involving substitution. So they start with a shopping example where they give us a model, and the question basically says, given f of x, which is equal to 42.2 times 1.56 raised to the x power, which models the average amount spent in dollars after shopping X hours. So this is the question. They want to know how much, so what amount will you spend after shopping 4 hours? That's the question. And so basically this is simply f of x is equal to 42.2 times 1.56 raised to the 4th power. So use your calculators. Let's see if we can all work this out. They want you to round to the nearest dollar. So to the nearest dollar rounded. So if you get, for example, which is what you're going to probably get is 249.92.556, you're going to simply round it to $250. Make sure you're able to do that in the calculator. That's all I'm asking you at this moment to do. And if you're cool with that, let's move on to example 2. Is everybody good?
249.9.
249.92556 is what I get. The main gist is that you raise the power of 4 with the 1.56 first, and then the last thing you do is multiply by 42.2.
Professor, is that an X at the top before the 2.2?
Yes,
I
up
believe
here, up here.
To the left of the 2.2, what is that? Is that like a cent symbol? What
Oh,
is
that's
that?
a dollar sign.
It's a
Oh,
dollar sign?
$sign, yeah, yeah. All right, example 2. If everybody's cool with that, that's merely substitution. Example 2, we're going to talk a little bit about exponential functions and their graphs. So there is a parent graph for exponential functions, which is the one they're asking you to graph. They're asking you to graph, in this case, f of x is equal to base 2 raised to the x. And that is the parent function that we need to learn for this. So quite simply, as we go through this example, actually, I don't even need that much space there. Notice that I'm focusing on the first and second quadrant of the x and y axis. All right, so we have x and y. Let's use 0 for center point. So I'll put 0 right in the middle. And I'm going to go 1 and 2, maybe 3, and going negative, negative 1, negative 2, negative 3. And so in essence, again, we're substituting because this is just 2 to the negative third, 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the first power, 2 to the second power, 2 to the third power. And our values, obviously, that ensue are 8 for this, 4, this is simply 2, this is 1, this is now 1/2, this is now 1/4. Remember, they're negative, so we bring them below the fraction bar. And so that's what we get. One of the keys or characteristics here is that we always start with the 0, because when x is 0, y will always be 1 if there are no transformations. When x is 1, in this case, you could see y will become 2. When x is 2, y will become 4. When x is 3, y will become 8. It's probably up here somewhere. And now as we go to -1, I'm half of this. At -2, I'm even less. I'm at 1/4 of this. And at 1/3, or -2 to the -3, I'm down to 1/8. So I'm reducing by a quarter each time practically. It will be asymptotic on this side. It rises to the right. And as I stated, it will go through without any transformations, no vertical shifts, no horizontal shifts. It goes through 0, 1 without any transformations. We will consider the range of this graph to be from 0 to positive infinity. And the domain, however, is not restricted. The domain is all real numbers. So it's from -infinity all the way to positive infinity. And that is the domain and range and some parts of the major characteristics of this type of graph. And so this continues infinitely this way and this way, respectively. Again, it'll look like it's going to touch the x-axis, but it never will. In this case, I also want you to focus on the fact that the base b is a 2. So the base b is considered greater than 1. So we will say then as a note that b is greater than 1, where b is the base of b to the x, right? And so that is the truth in this type of exponential function. Do you want to try to graph another base like f of x equals 3 to the x, or you got the general idea you think with this question?
What are you talking about? Like, I don't get where the b came from.
B is the base, the 2. That is the base, 2.
So where x is 0?
Not necessarily, it's just a base. I could give you another question, for example, and I could say to you, if I have f of x is equal to 3 to the x, that is the base, and that is raised to the x.
Oh, okay, cool.
Yeah.
I get it now. Thank you.
So the base is always your, in this case, your main number. And when the base is greater than 1, you have a graph that has the characteristics that I just showed you.
Oh, now that makes a lot more sense. Thank you.
So it could be 4 to the x, 3 to the x. That's why I asked you if you guys wanted to graph a 3 to the x.
So if the b is always greater than 1, it's always going to be asymptotic, and it's always going to rise to the right, and the
Correct.
domain and range. Okay.
Correct. Correct. Those are like characteristics that are innate to this type of function. Given the fact that that base b has to be greater than 1. And that base b cannot equal 1, by the way. All right. But what happens when the base b is a number that's fractional? So in other words, b, I don't want to say it's less than 1, it's just b is a fraction. What happens? So I'm going to go ahead and I'm going to do the reciprocal of what we just graphed to help you solidify the point. This is example 3. So we're going to graph the reciprocal of what I just did. So we're going to graph 1/2, that's your base b raised to the x. same thing applies. Here's x, here's y. I'm going to start with 0 in the middle. I'm still going to do 1, 2, 3, -1, -2, -3. And I want you to notice the numbers, because now this is 1/2 raised to the -3rd. The answer here is actually now 8. Remember, negative exponents, you flip them to make them positive, right? Here's 1/2 to the -2. Well, this is now actually 4/1. This is 1/2 to the -1. Well, this is now +2. This is 1/2 to the 0 power. Well, that's 1. Here's 1/2 to the 1st power. Well, that is 1/2. Here's 1/2 to the 2nd power. Well, here's 1/4. And the last one, 1/2 to the 3rd power. Here's 1/8. So if you remember in the prior example, they actually were inverted as far as the y's go. So what you are going to notice is that, yes, they still have the same characteristics. I'm actually going to bring this down. So here's your x-axis, here's your y-axis. So again, here's 0, 1. That is still going to be a key component. But now at -1, I'm at +2. At -2, I'm going to be at 4. And at -3, I'm going to be at 8. Somewhere up here. Notice that at +1, +2, +3, these are the fractional pieces. So that's 1/2, that's a 1/4, and that's an 1/8. And it keeps going in this direction. It decreases going this way. It's still asymptotic on this end. Asymptotic still goes through the point 0, 1 when x is 0. It drops from the left to the right, drops from left to right, none of that's changed. But that's a general idea of this function. So you have two conditions, either that base is greater than 1 or it's a fraction. We also refer to both of those that I just showed you as 1-to-1. These are 1-to-1 functions. The domain and range do not change. The domain is still -infinity to +infinity. The range is still from 0 to, in this case, is still infinity because it's coming from +infinity up here. All right. So do you want to graph two different graphs of that type, or do you want to just continue? It's up to you.
I feel that this is easy now, that it wouldn't require to graph another one, but I don't know about the rest.
Well, you tell me, whoever wants to.
I'm good.
You're good? Okay. So let's talk about shifts and transformation. So examples 4 and 5 are about that. So in example 4, they're asking us to use the graph where we have f of x is equal to 3 to the x And we're going to use that to graph g of x is equal to 3 raised to the x plus 1. And so what happens here is, if you notice, the shift in this case is taking us to the left 1 unit. It's a plus 1. So this is a horizontal. This is a horizontal shift. To the left 1 unit. So we start with our original graph, which is where we have the xy for the 3 raised to the x. So we would do this one over here. Again, use 0 to start, -1, -2, just for a rough enough graph, we could just stop at 2. So this becomes 3 to the -2, 3 to the -1, 3 to the 0, 3 to the 1, and 3 to the 2 with the original values. So this will give us 1/9, 1/3. This gives us 1. This gives us 3. This gives us 9. Now, if you notice, we're going to graph over here what I'll call y2, which is our 3 to the x plus 1. So I want you to notice that instead of 0, 1, I'm going to move to -1, 1. Instead of, so let me graph here so you see where I am. So I'll graph the original. Okay, we'll assume 9 is up here. Obviously, we're dropping this way. So this is the original in black. In green, I'm going to do the next set of moves. So I want you to remember, this point right here is going to go to the left. Remember, this point currently is 3, 1, right? And so my next point, if I move over here, I also have another point.
Professor, you said 3, 1 or 1, 3?
Yeah, it's 1, 3, right?
1, 3. It's called a brain fart.
Don't worry.
So this is 1, 3. This is going to now become over here because I'm moving 1 unit to the left. So now I'm at 0, 3 for my new point. This 2, 3 is now going to be, or 1, 2, 9 is now going to be 1, 9. This point here, which was 0, 1, is now going to be -1, 1. This point down here is now this point, and so on. So every point has adjusted 1 unit over, and that's our new diagram. So in essence, we have added or moved over 1 unit to the left. This became -1. This became -1, 3. This became 0, 3. So this became 0. This became 1. Here I'm losing 1, so this became -2. This became -3, and so on. So that was the shift that this resulted in, or your new x points as a result of that shift. Do you want to see it in Desmos? Or is that clear enough for you?
That's good for me.
It's good enough. If you want to show it, that's fine. But I understand it.
The key is that everyone understands it.
I hope so, because not everybody talks.
I know. So I need to know if you want.
I'm good.
You're good?
I'm good. Thank you. Mhm.
All right, let's look at example 5. Example 5 is very easy. Example 5 has also to do with transformations. The only catch in example 5, it's just simply a vertical transformation. So they want us to use the graph where f of x is equal to 2 to the x to obtain the graph. And now if you notice, you'll see why I say it's a vertical transformation. You're going to graph g of x is equal to 2 raised to the x minus 3. Do you see now why I say vertical? So it's a vertical drop of 3 units, basically. This also means that this is your new asymptote. In the original questions, I said to you that the diagram will be asymptotic to the x-axis, where y equals 0. Well, here, y drops. So if I start here at the x-axis, at this x-axis, this was the original asymptote of 2 to the x, because the original graph of 2 to the x, in essence, did this behavior and was asymptotic, and that was the asymptote, where y equals 0 was the asymptote. On this new one, because that's -3, my new asymptote is where y equals -3. So guess what? I already know that this point is this point down here. It's going to drop 1, 2, 3 units. Every y that you had originally is going to drop 3 units. So in essence, this will go through 2, 1. This will go through -1, 1. This will go through 0, -2. This will go through -2, -2 3/4. So it'll start to drop this way. And this is our new graph. All right, looking at the points, the original 2 to the x has xy coordinates, and I'm just going to do the 2's from -2 to +2. -2, 1, 0, 1, 2. Right, the original graph, this will give us 1/4. This gives us 1/2. This is 1. This is 2, and this is 4. The second y in green, this will be our, consider a y2, which is the equivalent of 2 to the x minus 3. Notice that all my y's are now going down 3 values. So this will become -2 to the 3/4, -2 to the 1/2. This will become down 3. So this will become -2 itself. The 4, remember this is 2, so this actually becomes 0. And no, this does not become 0. I'm dropping 3 units, so 3. So this is 1, and this becomes 2, 1. So this is a -1. Those are the new y values that I have described here. So for example, this point is 2, 1. That's this point here. This is our new y, the 1. The next point is -1, 1 right here, or 1, -1. This point is this point right here. 0, -2. That's our third point right here. And the rest are fractional points. You can see them right here. All right, Is that easy or do you want to try one? It's up to you.
I'm good on that.
You're not,
Good enough. It's not so different from the other graphs you have done.
no, not at all.
It follows the same pattern.
Pretty
Are we
much.
gonna be doing shrinking and stretching as well?
Maybe in some questions. I think that the next examples are about investments. We're going to talk about choosing investments. We're going to use
Investments.
yes, we're going to talk about the gray wolf population because that has exponential values. We're almost done. That's why I wanted to do the 2 units today. If you guys have the energy for it. So they introduce in the notes natural base E, which we know is 2.71828 repeating. And so the reason why they introduced this base is because we're going to talk about future value where you have the present value times natural base E, and natural base E is raised to the rate times time. Rate is always in decimal form. Time is always in years. So if they say 18 months, they're really saying 1.5 years. And this is a function in your calculator. Okay, so that's why they introduced that. They also introduced this with populations. Natural base E is used for populations. So they could give you a formula asking you to find out a value of something as an example. I know they go into the gray wolf example, and this will be example 6. And they basically are asking you to substitute. They give you f of x is equal to 1,145 e to the raised to the 0.0325x. And then they ask you to find the value of f of 36. So basically they're asking you to substitute. So use your calculator and just calculate it. Make sure that you know how to use these functions. That's all I'm asking you to do. And so that's all you got to do is substitute. When you substitute, your answer for this question, if I round it to whole numbers, should be 3,689 total. All right, so just take a look and see if you can do that real quick with substitution and you can get that answer. And then I'll move into example 7 and
Professor, this is like when it's like continuously increasing, right? That's what this is?
wolf population, yeah, because there's no limitation technically. We use natural base E for those types of questions.
Okay, thank you.
And usually that's what questions like continuous compounding or like populations. Oh, that's not perp, by the way. This just happens to be a function they give you. All you're doing is substituting.
What do you mean it's not per?
Yeah, the next one will involve PERT. I just was having a conversation with you. Make sure you can get to this number is all I ask you to do right now.
Yeah, I got it.
Super. All right, example 7. Now we're choosing between investments. Okay, so there's 2 formulas we're going to use. Formula 1 is for compounding periods. In this investment, they're going to ask you to use where A, or future value, is equal to the principal amount times 1 plus the rate over n raised to the n times t. N is your compounding period. Or if you have continuous compounding. If they ever say the word continuous compounding in the question, as opposed to quarterly or semi-annually, then you're going to use PERT, where I say future value is equal to the present value times E raised to the rate times time. Okay, and that is
This was also given on the previous class of algebra, right? I
yeah,
remember.
yeah.
Yeah. This was last class.
Yeah,
So
I used to go nuts on that.
okay, well now let's go nuts here. Let's talk about it. So in this example, they basically say you decide to invest $8,000 for 6 years and have a choice. So you can choose to invest in two accounts. The first account is, so I'm going to do like one. This is 7% per year, compounded monthly. The second one is continuously compounding with a rate of 6.85%. Which is the better investment? Okay, remember there was more information given to you at the beginning. So I'll set both of these up for you unless you want to try first, and then I'll set them up after you.
Can we try them first?
Try them first.
The 7% is better, right?
Not by much, but yes, it is.
Okay.
I'm
It's not.
getting
It's not by much. It's like by like. It's by like almost like $100, like $100.
give it $100.
Right. Okay.
Yeah. So this is what I'm getting in case anyone is falling behind on this one. So this one is simply A equals 8,000 E, and this is raised to the 0.0685 times 6. Because remember, they did give you this some investment information up here. you have to use. So this one is 12,066 and 60 cents. Are we good? Are we okay?
Yeah, I got those.
Super. Is there anybody having issues?
What were you saying earlier? Because I didn't hear this at all last semester. Just you were saying earlier something about if that it's always in years, and that if it's 18 months, it's 1.5 years.
Yes.
When would you do that? That's if they like if
Let me
t
say
is
18
like
months. If they
you
tell
you
you,
wouldn't put 18.
you would not put 18 because that's not in years.
Okay.
In years, 18 months is the equivalent of 1.5 years.
Okay.
So dare I ask, would you like to do 4-2 today? To use our time up wisely, or do you want to just jump into the homework and keep going?
I would like to do 4-2. Sounds good.
Let's do 4-2. Any opposing? No? Okay.
Yeah, we can go ahead.
4-2. Awesome. Yeah, this will help us with moving forward. And okay, this also ties together. That's why I wanted to do it together in a weird way, because we'll kind of tie a few pieces together. So this is logarithmic functions. This does have quite a few examples, and I'll still finish before I think of our second little time period here. Okay, so one of the first things that you need to know is what is a logarithmic function. It basically looks like y equals some log base b x. Okay, and all a logarithmic function is as an example. So let's say I said to you, I have log base 8 equals 3. Would that make sense to you if I said that?
Yeah, it's 2 to the third equals 8, right?
Mm-hmm. So I always tell
Yep.
you,
I
will
remember this from the
tell
past
you
too.
that base raised to the third power will give you 8. So 2 to the 3 equals 8. So one of the things that they ask you to do in example 1 is they say to you, write each equation in its equivalent exponential form. All right, and so one of the first ones they give you is in part A, they say 2 is equal to log base 5 x. So if you follow this example I gave you, the only change I'm going to ask you to do is always put the equals 2 on this side, because then I can follow that logic of 5 raised to the second is x, so therefore x equals 25. Does that make sense to you?
Yeah.
Okay, example B, kind of similar question. They give you log base b of 64 is equal to x. I'm sorry, is equal to 3. So that means that that base raised to the third power is equal to 64. So b, some number b to the third power is 64. Let's pretend we don't know that that is 4. We know it's 4. We're going to take our calculators and we're going to say, well, then that means that b is equal to the log of 64 divided by the log of 3. And when you do that, you should get 4. Try it on your calculators. Is it 4 times 4 times 4, 64?
I mean, it gives me 3.7855.
Me too.
Does the mode have something to do with the mode on the calculator has something to do?
Yep. Let me see. I'm going to try it on my calculator. I'm using a cheap calculator. I don't have my good one with me, but yeah, you should be getting 4. That's what I'm getting, even on the cheapie.
I tried it on 2 calculators and I'm getting the same result, 3.7855.
Yeah,
Take-
I'm getting the same thing.
I'm getting this, I'm getting the same thing, 3.7855.
I'm
Well-
trying on a TI 83 Plus and a TI 30.
Yeah, even
Yeah.
with changing your mode?
I mean,
What mode?
Change your mode?
The what?
Whatever mode you are in, change it.
right now I'm in Greece and normal. So,
Me too.
Okay.
oh no,
So you're
private
gonna
gradient.
put.
Is everyone having that same issue?
I am.
Do you know that 4 times 4 times 4 is 64?
Yeah, of
So you know that the answer should be 4 then, right?
course.
Yeah, okay.
But I know like when we have to do it with like different, like it's gonna get more complicated.
We're gonna practice this process. Right now that I'm not gonna focus on that right now,
Okay.
but we'll go back to it. Here's the last example they give us. Log base 37 is equal to y. So as an exponent, an exponential form, this would be 3 to the y is equal to 7. You can't really solve for that per se. Okay, I think I know why this is not working for you. I think I know why.
It should be natural logarithm.
Try it, see if that makes a difference. I'm just curious. No, you still got 3.78. But here's what I'm suspecting. Let me before I just say something. Let me just double check what I'm saying.
If anything,
Is there a way to try it to get a different whole number? Maybe you just have to round to the highest whole number.
That's possible. Can we agree on something like this? I think what it is, I got my wires crossed and I'm showing you wrong, something wrong here. I don't think this actually works like this. This actually works here. When you're solving for like an exponent like this, like a y equals. This would be log 7 over log 3. Try that and tell me if you get 1.77 and change.
177. Yeah.
Okay, so let's use some common deduction here. We know that 3 to the second power is too big. We know that 3 to the first power, well, that's too small. And a 1.77, that might be just what we need. So in other words, 3 raised to the 1.7712437749, blah, 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 all of that, that should give you 7. Try it.
Yeah.
I'm guesstimating it. So yes, when you
Yeah.
do this, you do get 7. That's what it was. I'm sorry. I got excited and I went to,
It's okay, Professor. It's okay.
I crossed wires. All right. Are you guys cool with those 3 examples, or do you want to see 3 more to try?
I'm good on that.
I mean, if we wanted just to get let's say that we don't know what that 4 would be the answer, well, you can just get the whole number and get the cubic root out, the cubic root, no? Like the cubic root of 64 would be 4.
Yeah.
So
So
we can just reply by that.
b cubed is 64. So take the cube 1/3 root or cubic root on both sides. So that will cancel with this, leaving you b is equal to 4.
Yeah. So.
Yep, that would work. But this is the process I was trying to throw your way. All right, awesome. So that is going from logarithmic to exponential. So we're going from logarithmic to exponential in this example. In example 2, we're going to go from exponential to logarithmic. So the question stem says write each equation in its equivalent logarithmic form. So in part A, they give us 12 squared equals x. And so in this case, our exponent is our answer. Our base is 12. X is the number we're looking for. Remember, if I have 12 squared, well, that's equal to my number, which is 144. The base raised to the power is the number, right? All right. In part B, they're giving you b to the 3rd is equal to 8. Again, if I'm expressing this, I'm going to say the log of the base b of the number 8 is equal to 3. In other words, one number raised to the 3rd power is going to give me 8. Okay, and now the last example they give us, part C, they give us e raised to the y power is equal to 9. So log of the base e, number 9, is going to equal y, because e raised to the y is our 9. And that is how you check it back.
Professor, where does the constant e come from? If you
The natural base,
yeah.
there's a whole history for that. There are books written on just that, believe it or not. And it's basically a formula. You asked, you shall be answered.
Suffer.
No, you shall suffer. No. It's basically 1 plus 1 over n raised to the nth. And we found mathematically, it has been found that this is in nature, innate in certain patterns, like patterns where you don't know. Like, for example, the world population. We can estimate the world population on a given day, and that next minute that we estimated it, it's changed. Because people have died, people have been born.
Yeah.
So whenever you have that kind of fluctuation where we just constant change, that's why it's continuous. It's a continuous, one of our continuous equations. It measures continuous patterns in populations, anything financial that is continuous, that kind of thing. But there's books. By the way, if you really like to nerd out, there is a book. Good luck finding it because it's a paperback. It's by Mario Livio. What a great book. If you like philosophy and you like talking about, you know how people love to argue about religion and mathematics and sciences, and this book, it talks about phi, which is called the God's number,
Mm.
phi, and
Yeah.
it talks about the different patterns in our nature. What a fabulous tie to, first of all, it's related to this units. It's all about logarithms if you think about it. But just like the snail structures,
Yeah.
like conch structures, flower
It's found everywhere.
petals, yeah. That ratio is in flower petals. It's in nature. It's in our planetary alignment. A lot can be discovered there. All right. So how are you with this example, example 2, and example 1 so far?
Yeah, good.
Cake?
Mm-hmm.
Example 3. Now, example 3 is evaluating logarithms. I would have a calculator at this point, whether it be your phone or any other. They simply ask you to evaluate. And they give you the following. So for part A, they give you log base 2 of 16. What do you think that answer is?
I mean, it should be 4, right?
It would be 4. So always finish it is what? So in other words, 2 to what power is equal to 16? We know x is equal to 4. If we didn't do that, go to your calculator, do log 16 over log 2. Please tell me you get 4, because if you don't, I'm retiring tomorrow.
I got 4.
Okay. Awesome. In part B, you have log base 7 of 1 over 49. Again, always finish these questions with equals what? In other words, 7 to what power is 1 over 49? Now, you know, if you know your multiplication tables, you know the 7 squared is 49. But this is not 49, this is 1 over 49. So this has to be?
-2.
-2. Okay, for part C, they give you log 25, 5 equals what? They don't give you the equals what, I'm telling you to put equals what. Now we know 5 squared is 25, so the square root of 25. So 25 to what power? 25 to what power is equal to 5? So you should get x equals 1/2. Right? Because that's the square root of 25. Square root of 25 is 5. Okay, and in part D. In part D, they're giving us log base 2, fifth root of 2. right? So that means that in this case, 2 to what power is equal to 2 to the 1/5, which is the equivalent of this. Those are the same. Because you have the same base, then that means that x equals 1/5. It's one of those properties. How easy was number 3? Example 3.
It was easy. The only thing that I got a bit of confused for a bit was the example D.
The
Yeah, me
last
too.
one.
I got everything but that one. That one, like, I mean, I've seen it before. It's been a while.
Just remember, if this is a root, and that's the 5th root, you can write a root as an exponent as a fraction of that root. So if this is 5th root of 2, then this is 2 to the 1/5. And if you have the same base, then these two have to match. Okay. This is notes. This is notes. So we're going to look at basic, logarithmic properties. Nothing, I don't think much of this is new to you. So here's what we know. We have log base b of the number b has to be 1. The reasoning behind that is because this number to the 1 power will be that number. So in other words, b to the 1 power is b.
What is that? Okay, does that log to the what is that? Not
Log
an
to the
X?
base b, log to the base
Oh,
b
okay.
of b is equal to 1 because b to the 1 is b.
Yeah, sorry. She said I write everything down, so I just wanted to know what that was.
That's cool, that's cool. The second property that we need to know, and by the way, these are properties involving 1. Involving 1. Is log base b of 1 is equal to 0. And that is true because b to the 0 is 1. Anything to the 0 is 1, right? So those are just two properties that they want you to know. And these two properties are going to now tie to example 4. So the first one is evaluate. So the first one is log base 7 of the number 7 is equal to what?
1.
1. Because 7 to the 1, ask yourself, 7 to what will give me 7? 7 to the 1 power will give me 7. Okay, in example B, they give us log base 5, 1. That's all they give you. You have to remember to put the equals what. 5 to the what power is 1?
0.
Yeah. So that means x is equal to 0. And that's all they ask you in that one.
Okie dokie.
Easy, right?
Yep.
All right, example 5. Example 5 is also inverse properties of logarithms. So inverse properties of logarithms. Now, you guys should know or remember how to change or go to find an inverse of something. So what they do is they say to you, well, if you know that f of x is equal to b to the x, and we're trying to find its inverse, we know that step 1 is that y is equal to b to the x. So basically change f of x to y. The second step, we swap x and y. So this is really x is equal to b to the y. In the third step, so remember this is swap. This is f of x swapped to y. Okay, and now here we solve for y. So we know that y is equal to the log base bx, and therefore this is the inverse. So if I write this as an inverse, this looks like this. Having stated that, some inverse properties of logarithms are also easy to identify. So the first one they give us is that if I have a log base b of the number b raised to the x, then the answer here has to be x, because b raised to the x is equal to b raised to the x. And the second property they want us to identify is that if I have b raised to the log base bx, then the answer here would have to be x itself, because everything else cancels. With that said, let me give you these two examples. So example that will tie to this one would be example 4, where they ask you to, or example 5, they ask you to evaluate log base 4 of 4 to the 5th power. Well, that answer would have to be 5, because 4 to the 5th is equivalent to 4 to the 5th. The other example they give you is this one, where they have us look at log 6 raised to the log base 6, 9. What happens is, and the reason why the answer is going to be 9 is because log 6 and 6 cancel, and it gives you 9 as a final answer, and that is the answer. That's simple.
So if you have a base and
It's raised to the log of that base,
it's canceled.
it cancels. Because it cancels to 1, really.
Yeah.
Okay. Are you cool with these two examples? They're just, that was example 5 here. And example 4. They're both example 4 and 5 deal with properties. That's those two right there. Okay. Now, example 6 has to do with inverses and graphing. So let's talk about how they're related. Now, in example 6, one of the things that I want you to take away from this is to understand that these graphs are inverse functions. So if they ever ask you to graph, like in this case, f of x is equal to 2 to the x, and they ask you to graph where g of x is equal to log base 2 of x, and they want you to graph it in the same coordinate system. Once you have this graph, you've already got this graph. If you don't believe me, watch the magic. And I'm just going to do the coordinates.
Professor, when they ask you for the g of x equals log 2 to the x, that's like them asking you for the inverse. It's the same thing.
Right, because this one is exponential and this is logarithmic.
Okay.
And they're inverse functions of each other. So watch what I mean. So let's go ahead and let's go from -2, -1, 0. Let's do 1, 2, and let's do 3. 3 is easy. So I'm going to graph the f of x one here, or at least come up with the numbers. So this is going to give me 1/4, 1/2, 1, 2, 4, and 8. All right, because remember, I'm just substituting all the x values into the function. The function g of x, I want you to follow the color. This is going to be my logarithmic function. So my g of x, I want you to notice that I'm technically going to just take the x and take the y, and I'm literally going to swap them. So this is going to be my -2, -1, 0, 1, 2, 3. And on the opposite end, I'm going to have the 1/4, the 1/2, the 1, the 2, the 4, and the 8. If I put them on a graph in purple, I'm going to graph the 0, 1, the 1, 2, 2, 4, and 3, 8. Okay, and that comes this way. Remember, these are inverse one-to-one functions, so you can get away with this. In red, I'm graphing its inverse. So basically, I'm going to have the following points. I'm going to have 2, 1. I'm going to have the graph 4, 2. 5, 6, 7, 8, 3. Coming down this way, I'm losing ground. And so this is going like this. These are the two inverses of this. And the x equals y is always going to be like my slant asymptote. It's going to sit between these two guys. Just remember that they are inverse functions of each other, the exponential and logarithmic. So I would always graph the exponential first. And if they want the logarithmic function, then I'll take the exponential and swap x and y, and I've got my graph. Remember I said to you that the 2 is the base? Look at your base. Would you like to try one of these? Or do you feel comfortable?
I'm good.
Yeah.
All you have to do is just like evaluate the first graph and then just swap it.
I would always evaluate the exponential function first.
Right.
And then swap it. And if they ever came up to me and they say, hey, which I actually took a test recently for personal gratification, they said, here, graph log base 3x. And I'm like, yeah, right. I'm like, no, I'm going to graph basically 3 to the x first. And then I swap.
Right.
And that's what I did.
Now, would they ask you to do inverse and transformations together?
Yeah, guess what's next?
Oh, I would have never guessed.
Never. So we have vertical, horizontal, reflection, shrinks and stretches, horizontal stretch or shrink, vertical stretch and shrink. And so what they're asking you to do in these questions really, in example 7, because I don't think they really get it deeply into that graphing. They're asking you to find the domain of a logarithmic function. Okay, and so they say to you, given f of x is equal to log base 4 of x plus 3. So the first thing you'd want to do if they ever gave you a question like this is focus on this x plus 3 right here. And so I would take x plus 3. We know it has to be greater than 0 because we don't have negatives in logarithms, right? So if that's the case, then x has to be a value greater than -3. So that means that my vertical asymptote, so at -3, x is -3, I have a vertical asymptote which blocks my equation. And I know also based on just selecting some points that this has to graph something similar to this. That's horrible. Let me draw that again. So it should be going through here. It should be going through here. It should look something like this. Because remember, to find x, if this is x, this is y. Your thinking is 4 raised to what power is going to equal this x plus 3? And that's in essence what you're thinking. So the easiest way I can tell you is if you just know that when x is -2, and you plug this into the equation, you know that y has to be 0, right? Because 4 to the -2 is equal to -2 plus 3. Mathematically, this is going to give you the equivalent of 1/16 is equal to 1. The only way that happens if if y is 0. So at -2, 0, you kind of have to evaluate that for yourself. And here, if x is 0, then you have, in essence, 4 to the 0 is going to give you that 3. You end up with 0 plus 3. And so just a little, actually it's not even 1. It's going to give you a weird, kind of a weird fraction, but you get the idea. The general idea is this will have this behavior.
Professor, can I ask you a question? Could you do for the graph of 4 to the x and then do its inverse and then get all the x values and subtract them by 3? Can you do that?
For this one?
Yeah.
Yeah, I think you could, potentially. Potentially, because this is y equals log base 4 of x plus 3. As you plug in values for x, you're solving technically this is now 4 to the y is equal to x plus 3. So as you plug in values, I guess you could use them a little easier that way.
Okay.
Yeah, that will work. All right, example 8 is a waste of time, but I'm going to do it anyway. And example 9 is equivalently kind of a waste of time because the way they just give you a model. You're modeling the children height of children. You don't have to find it. They're going to give you the formula. You're basically substituting, which is why I say it. You guys know this already. So they're telling you this kid, the height of this child can be modeled by f of x equals 29 plus 48.8 log x plus 1. And they want to know the percentage of the adult height this kid has reached by age 8. Basically substitute in 8. So you're going to do f of 8 is equal to 29 plus 48.8 log of 9, right? 8 plus 1, 9. You should get approximately 76. So they've reached approximately 76% of their adult height by age 8. That's all that is substitution.
Are there a lot of examples left in this section?
No, 9, 10, 11. Example 9 is another one that's kind of a waste of time, but
Hi.
what's the matter? This is, you need to go buy a new notebook. This example is earthquake intensity. And they give you this formula where the Richter scale or the magnitude R is equal to the log of the intensity of a major earthquake over the initial intensity of a almost zero earthquake. Now, little earthquake background. I don't know if you know this, but underneath us, whether we want to emotionally admit this or not, the ground is always moving. We may not feel it because the intensity is very low, but there's always movement in the ground below us. They call it a barely felt zero level earthquake, which we're experiencing every day as we speak in a normal situation. So what they tell you is that in 1906, there was an earthquake with the intensity of 10 to the 8.3 times as intense as a zero. This is a zero level earthquake. Everybody gets really quiet when I say that. Okay, so that means that this basically is R, the magnitude is equal to the log of 10 raised to the 8.3 times that initial intensity earthquake over the initial intensity. Notice that these are obviously going to cancel. Notice that this is log base 10, 10. So technically log base 10, 10 cancel each other out. The magnitude of this earthquake is 8.3. That's all you need to know there. You can literally look at this question and answer it just right there. Just understand this is a formula that make you go through. Is that ridiculous or what?
It is.
Extremely.
It's worth
Yeah. Okay. I could technically skip example 11 because it's another substitution question, but number 10 I want to definitely show you. So example 10 is finding the domains of natural logarithm or natural logarithmic functions. Okay, so they start you with the first one where f of x is equal to the natural log of 3 minus x. Okay, so if you notice, the first thing I'm going to tell you is focus right here immediately. You know that 3 minus x has to be greater than 0. So that means that x has to be less than 3. As a diagram, we know that 1, 2, 3, at 1, 2, 3, we have a vertical asymptote, and our diagram is going to take off in this direction, going this way, because x has to be less than 3.
Is ln always like e or something like that?
It kind of has the same behavior, but no. It depends on your diagram. Like in this one, when you set it greater than 0, remember math-wise, this is what you have initially for this one. You had a subtractor 3 on both sides, and that leaves you with negative x is greater than negative 3. But when you multiply by negative 1 to make the x positive, this has to become less than 3. So it switches it. So it depends on your equation is what I'm saying. Look at the next one. You have h of x is equal to the natural log of x minus 3 squared. So x minus 3 squared, we know that if I take x minus 3 and I set it greater than 0, then x has to be greater than 3. So that means that this can be all real numbers except 3. So it goes from negative infinity to infinity with 3. So let's say this is 0. Here's 1, 2, 3. At positive 3, I have a vertical asymptote, and so this will cut out this way and this way respectively because it's squared. There's got to be the positive and the negative of it. Always. I would
Can
not.
you repeat what you just did? I lost you with the that
Okay.
last one.
So
Sorry.
this is squared, right? So when we solve for this, we're going to take x minus 3 and we're going to set it to be greater than 0. But remember that you have to deal with the fact all real numbers except 3. So it could be less than 3 or greater than 3, but not 3. So yes, when you solve for this, you get x is greater than 3, but there's also the condition that x could be less than 3. So you have to take into both, and that's because it's squared.
Okay, thank you.
Remember when you take the square root of something, you take the plus and minus of it, right?
That's what
Yeah.
I'm thinking about when you're saying that.
Yeah, that's basically the gist of it. That's it. You've done the 2 sections for 1 and for 2, which is awesome. Let me stop the video here.